Problem 24. Call a positive integer fair if no digit is used more than once. It has no zeros and no digit is adjacent to two greater digits. For example, 196, 23, and 12,463 are fair, but 1,546, 320, and 34,321 are not fair. How many fair positive integers are there? So the question is asking the fair numbers, or fair positive integers. They have no zeros, then the digits cannot be used more than once, and there are no digits with two greater adjacent numbers. So, for example, for 1546, 5 adjacent numbers are 1 and 4, so it works. However, if you get 4 adjacent numbers, which are 5 and 6, they're both greater than 4, so they cannot be a fair numbers. Then how do we solve the question? Well, first we know that we can only use one numbers per digits. So we can use all the way from 1, 2, 3, 4, 5, 6, 7, 8, 9. We can write numbers until maximum 9 digits. Then we should look at starting from the first digits. So imagine the number only has one digit. Then the overall possible fair numbers are 9. It's 1 all the way to 9. And then for the second digits, we can choose 9. We can choose 2 out of 9 numbers. And then we can even switch. For example, if it's 23 is a fair number, and if we switch 2 and 3, it's 32, which still works. So there will be 2 possible ways if we choose 2 different numbers. Then let's check the 3 digits. If we have 3 digits, for example, let's say we have 1, 2, and 3. These are all possible digits if we have 1, 2, 3. Let's look at the first one. 1, 2, 3 is a fair number because there's distinct digits, there's no zero, and 2's adjacent digits, 1 and 3, they're not both bigger than 2. This works. The 1, 3 also works. However, 2, 1, 3 doesn't work because 1's adjacent digits are 2 and 3, which are larger than 1. So we cross out this case. This is the same as 3, 1, 2. So if we have 3 digits, we got 4 out of 6 possibilities. And then if we look at the pattern, we can see that the possible numbers, if we choose a number for digit, doubles. Now we can know that if there's a 4 digit, there can be 8 possibilities for 4 distinct numbers. Then by using this, we can say that n digits out of 9 digits times 2 to the power of n minus 1. This is the possibility for every single digit case. So we need to now have a sum for 9n times 2 to the power of n minus 1. Starting from 1. Then how are we supposed to have all the sum for the possible values? So there's a trick. First, let's try to make 2 to the power of n minus 1 to 2 to the power of n. Then this can be changed to 1 over 2 times 9n times 2 to the power of n. Then there's a binomial theory, which is this. If this is x plus 1, then the power of n, this is equals to all the sum of n from 1 to 9. If x plus 1's power of x plus 1's power of n is equals to sum of all possible values starting from n is 1 all the way to itself times x to power of n. Then this is similar to the equation we got. Then if x is 2 and n is 9, the case works. So 3 to the power of 9 equals to this. Sorry. But however, we counted this case from 0. Sorry, my mistake was that it starts with 1, but it actually starts from 0. So we need to eliminate 1 from this equation because our sum starts from 1 when the nth value is 1. So this is the value of the overall sum for the possible cases. 3 to the power of 9 is equals to 19,682. Now if we, sorry, my mistake, it's 19,683. And if we minus 1 from the value, it's 19,682. And if we divide this by 2, the value will be 9,841. Therefore, all the possible cases for fair positive integers are 9,841, which is C.